This lesson is for FST, lesson 8.5 on geometric series. We recently talked about arithmetic series. A series is going to be the sum of the terms in a particular sequence. So today our sequences are going to be geometric in nature. So if you take a geometric sequence and add up the terms, now it's called or referred to as a geometric series. Students will need a graphing calculator to do most of the questions in this lesson. The formula you're going to use to add up the terms in a geometric series is the first term multiplied by 1 minus the ratio between the terms to the n. Notice in the explicit formula it's r to the n minus 1. In the series equation it's just to the n. And then you divide by 1 minus r on the bottom. Keep in mind that when it's a fraction, there are imaginary parentheses on both the top and the bottom. The last thing you should do is divide. There is one exception to this formula, and that is when the r value is greater than 1. The formula can be modified so that you get less negatives. Only when the r is greater than 1, you can switch around the 1 and the r to the n, or the r on the bottom. So I think what I'll do today in the video is only illustrate the first equation, but then I'll go back at the end and point out that you could have used this formula on certain questions. So we're just going to do a bunch of examples. First example has the terms of a sequence listed together with plus signs, so that is indeed a geometric series. We also know it's geometric because it's pretty clear here that we're multiplying by 3 each time. So we could figure out the terms of the sequence first and then add them up, which would be what I would recommend. 4 times 3 there is 12. Make sure you do the order of operations here. 3 squared is 9 times 4 is 36. 3 cubed is 27 times 4 is 108. 3 to the 4th is 81 times 4 is 324. So you could literally just type these into your calculator because it's a sequence that stops. This is the last term that we're going to look at, so we could just add those up. The first thing they want us to do, however, is to rewrite it using sigma notation. As soon as you see a sigma showing up, that's your hint that you're dealing with a series, because sigma problems always mean add up the terms. So we need to pick a variable, usually n or x works well. We're starting with the first term, and then we need to know what term to stop at. So let's count how many terms we have in this case. 1, 2, 3, 4, 5 terms. So the 5 needs to be on top of your sigma. Then you need a formula that would generate the terms of this sequence. So we use the explicit formula for a geometric sequence, and we put that right in front of the sigma. The first term is clearly a 4. And from this one, it's pretty easy to see that we're multiplying by 3 each time, so 3 is the r value. Now in the explicit formula, we do raise to the n minus 1 power. If we were doing our new formula today, we would have just raised to the n. So that's all you need to write for rewriting it in sigma notation. Know that what we just wrote with the sigma is the same as the original problem that was given to us. One's written out with plus signs, one's written out with sigma. Then they want you to evaluate the first 5 terms added together in the series. So we already know if we added all of these up by hand before, we know that it's going to add up to 484. But let's try it using the formula that we're using for today. So g sub 1 is a 4, the r is 3, and we're raising to the 5 because there's 5 terms. Be careful here when you raise to the power, it's not 1 minus 3 in parentheses to the 5th, only the 3 is being raised to the 5th, so you put your parentheses on the outside. And then on the bottom 1 minus 3 again. When you type it in, you should be able to type it in all in one step if you include parentheses on the top and the bottom. So try typing that in. I'll do the same on my calculator, and hopefully when you're all done, you'll get the same answer that we got, which would be a 484. So try typing that in on your graphing calculator or your scientific. I'm going to show you what I did on mine. I originally had parentheses around the top, but the calculator eliminated those when it actually calculated. Notice where the 5 and the last parenthesis lie. The 5 is on the inside of the parenthesis, not on the outside. If you didn't get 484, then you must have typed something in incorrectly. So we got the answer we expected. So know that in those situations you can either add up the terms, or if it says use a formula, then we're going to use the formula. Either way, we should get the same answer. Let's try it again when the numbers aren't quite so easily figured out. This one, it's kind of difficult to see what we're doing to get from one term to the next, so we're going to have to do a little calculating there. Remember that when we don't know what the r value is, we can just divide the second by the first to figure that out. So if we do 4 divided by 6, that reduces to 2/3. So then I just verify that 4 times 2/3 gets me 2 2/3, and it does. Because 4 times 2 is 8, 8 divided by 3 is 2 2/3. So my r value there is going to be 2/3. I'll need that when I do my evaluation on the bottom here. They want me to rewrite it in sigma notation. So again, we need to pick our letter. I'm going to choose n. Need to figure out how many terms I have. Looks like there are 6 terms this time. And then I need a geometric explicit formula to sit in front of the sigma to generate the terms of the sequence. First term is a 6. I already determined that the r value was 2/3 by dividing the second by the first. And then I raise to the n-1 power. Now when I evaluate the series, I go back and I use my new formula from today. So I take the first term, multiply by 1 minus 2/3 to the 6th over 1 minus 2/3. This one gets a little bit trickier to type in because of the presence of the fraction. If you're using the fraction button, that'll definitely help you. If you're using the division bar to do your fraction, you'll probably want to insert some extra parentheses around the fraction itself. So give that a try on your calculator. You should get about 16.4. So type that in, pause the video, see if you get 16.4. If you don't, unpause the video and I'll show you what I get on my calculator. And I'm not quite sure where the brackets came from. The brackets are not necessary here. I think I might have just used too many sets of parentheses and the calculator got a little confused. But the setup is still what it should look like regardless of the brackets, and I should get 16.4 there for my answer, which is what we anticipated we would get. Another type of question they may ask you is when they give it to you in sigma notation. So we can tell by the look of the equation that it is indeed geometric in nature, and then because of the presence of the sigma, we know it's going to be a series. So if this is a geometric series and I'm evaluating from 1 to 6, I can utilize the pieces that I've got here to either generate the terms of the sequence and then add them up by hand, or I can do the new formula from today. It'll generate the terms and add them up for me. So I'm going to do the new formula from today. So I'm going to use 24 as my first term, 1 minus 1/3 to the 6th because there's 6 terms, and then 1 minus 1/3. Again, this one has fractions in it, so it's a little bit harder to type in on your calculator. When you're all done there, you should get about 36. I think I got 35.9 there. Just as a point of interest, if you wanted to generate the first 6 terms, you could just take the explicit formula, fill in a 1, 2, 3, 4, 5, and 6, and if you did that, you'd get the list that I'm going to give you here. And so the first 6 terms of this sequence would make 24, 8, 8/3, 8/9, 8/27, and 8/81. So if you added those up, you should get the same answer of about 36. But clearly, it took me a long time to come up with those. I had to do a whole lot of work to do it. So doing the formula here got us our answer much faster. Let's do a couple word problems. Recall the disease outbreak from lesson 8.4. We did that in the video. This time, assume that the first week there are 14 cases, and each week thereafter the number of new cases increases by 25%. The presence of the percent automatically indicates that this is geometric in nature. That is one skill that students will want to get good at because the arithmetic and the geometric situations will be intermixed on tests and quizzes. So we know it's going to be geometric in nature. The percent is going to be our R value. If we just multiply by 0.25, that's actually going to decrease, and it clearly says that they want us to make it so that it increases. So a reminder here that you want to do 1 plus the percent when it's increase. If it was decrease, we would do 1 minus the percent. So we know that our R value here is going to be 1.25. So we'll use that in a little bit. Next, use the sigma notation to express the number of people infected by the nth week. Again, it's implied here that we're trying to find the total number of people infected, not just the new cases. So there's an implication here that this is indeed a series. It's also a series because they want us to use sigma, and sigma means we're adding up the terms. So I'm going to do a sigma, and I'm going to use letter n, mostly because they told me to. And so the n's are going to go from 1 to n, and then I need a formula for the sequence. The first term is 14. The R value is 1.25 because of the percent, and then I raise it to the n minus 1 power. How many people have been infected by the end of the 5th week? I want to know the total there, so I would indeed use the new formula from today. First term, 1 minus 1.25 to the 5 over 1 minus 1.25. Breathe a sigh of relief here because we are not doing fractions on this one, and so this one will be a little bit easier to type in on the calculator. When you do, you should get about 115, and we want to say people here. So pause the video, give that a try, type that in correctly. One more example to try, word problem. This one's cool because it's a real life example, something we can all relate to. Maximum number of natural ancestors that you could have are 2 parents, 4 grandparents, 8 great-grandparents, and so on. Assuming that no one appears twice in your tree, how many generations must you go back before you'd have 1,000,000 ancestors? So on this one, again, what are the implications for it? We start out with 2, and then each time to get from one term to the next, we're doubling. So 2 is our first term. And then because we're doubling, that automatically means we're doing geometric. And then because the number of ancestors means that we are adding each time, that automatically means it's a series as well. So we're going to do 1 minus the R value. We don't know the n this time. And then we do 1 minus the 2 on the bottom. And we're trying to get to 1,000,000. So now what we're going to do here is solve for n. So this is a little bit different question from any of the others that we did earlier. So the first thing that happens is we have 1 minus 2 on the bottom, which is going to be a negative 1. I could simply make this 2 a negative to compensate for that. Or because it's solving, I'd be more comfortable getting rid of that negative 1 by multiplying by negative 1 on both sides. I'm currently dividing by a negative 1, so to get rid of it, I'm going to multiply by negative 1. So I end up with negative 1,000,000 on this side. Now the thing that's the furthest away from the n is the 2 that's out here, so I'm going to divide by 2. And then I'd subtract 1 from both sides. The 1 is not being subtracted right now, it's the 2 that's being subtracted, so I want to take away 1 from both sides. And then, because both sides are negative, I'm just going to change everything to positive. I haven't changed the value of anything, I've just said because it's negative negative, then I can just change it to plus plus. Now at this point you've got 2 options. You can either solve using logs, and we will be learning about logs later on. So if students remember how to use logs from algebra, they're welcome to do that. If you don't remember how to do logs, then you'll simply have to do trial and error. So you'll have to find values for n that get you as close to 500,001 as possible. It will be a double-digit number, it will be a number less than 30. So when you're all done doing that, unpause the video. And you should have gotten about 19 generations.